Our speaker for this session is Dr. Lisa Federer. Lisa is the National Library of Medicine Data Science and Open Science Librarian. She focuses on workforce development for data science and open science in biomedical research and library communities, as well as advancing data best practices to enhance research reproducibility and to promote data reuse. Prior to joining NLM, Lisa spent 5 years as the research data informationist at the National Institutes of Health Library, where she developed and ran the library's data services program. In addition to publishing numerous peer-reviewed papers, she is the editor of the Medical Library Association Guide to Data Management for Librarians. She holds a PhD in Information Studies from the University of Maryland and a Master of Library in Information Science from the University of California, Los Angeles, as well as graduate certificates in data science and data visualization. Her research focuses on quantifying and characterizing biomedical data reuse and development of meaningful scholarly metrics for shared data. So Lisa knows all things data, I think is what we can get here and what we can learn from her today. The title of her talk is Beyond the Paper, Sharing an Impact of Digital Research Objects. Please use the chat feature to ask any questions that you have, and we will go over them and answer them at the end of the session. Microphones are muted, so you don't need to worry about that. But we'll monitor the chat, as you're welcome to use it as we go, and I'll do my best to make sure that I keep track of the questions so we can ask them when Lisa is all finished. Everyone, help me welcome Lisa Federer. Thank you so much, Lisa. Go ahead and take it over.
Thank you, Heather, and thank you to the rest of the organizing committee for the invitation, and thank you all for being here. There we go. As Heather mentioned, I am the Data Science and Open Science Librarian at the National Library of Medicine in the Office of Strategic Initiatives, and I really like data, and I'm here to talk about some of the considerations for research outputs beyond just what we may have typically worked with in terms of scholarly papers. So what I plan to cover today in the time that we have together is talk a little bit about what I am meaning when I talk about digital research objects, not just data, but other sorts of outputs of research as well. Introduce a couple of policies for sharing, some that have been in place for a while and some that are new or forthcoming. And then I want to talk a little bit about the sort of broader biomedical data ecosystem and some of the challenges and opportunities that we have ahead of us. And then just really briefly touch on quantifying impact of digital research objects and why this is important. So you are all probably very familiar with the sort of traditional scientific communication or scholarly communication sort of timeline. So as a researcher, I develop a hypothesis about something that I want to test. I collect some data to answer that question. I analyze that data, and then I ideally report those results to the broader scientific community and the general public. Most of what we have typically dealt with as the output of scientific research has really focused on this very final step, this reporting results in terms of the output of the scholarly paper. But there's a lot of other outputs and, sort of ephemera, if you will, associated with the research process that have also other valid uses and other importance to science. And when we talk about sort of this more open scientific communication, we talk about bringing forward some of those digital research objects that are collected and used as part of this research process, but in the past typically have not been made public. They've been closed in labs. They've been, saved on the PI's computer. So things like the data sets that are being collected as part of this research process, and also the software and code that are used to analyze that data. So again, when we talk about this sort of more open paradigm of scientific communication, we're not just sort of privileging the scholarly paper as the only, important output of the research process. We're also talking about these other sort of intermediate pieces as well that have importance and, deserve to be shared and have relevance to the broader scientific community. So we'll talk a little bit more about what those pieces are and how all of that works. So I want to start by talking a little bit about what this sort of biomedical research data ecosystem looks like, and what we're talking about when we're talking about sharing data. And by the way, I will probably say sharing data quite a lot during this presentation because it's a lot shorter than saying digital research objects. But you can assume that I'm also referring to that software and code that I also talked about. So the sort of data, code, software, all of this together. So we're at a situation or a point in time now where we have faster and cheaper technology than ever before. So we're able to gather a lot of digital data very quickly. This is a couple years old now, but this is a chart that shows the cost per human genome to collect or to sequence a human genome. And you can see that the first human genome that was sequenced as part of the Human Genome Project costs quite a lot to sequence. But as time has gone on, the cost to sequence genomes has dropped quite a lot. So we now are at a point where we can sequence a single human genome in about 24 hours and for about $1,000, which is drastically faster and cheaper than where we were even 10 years ago. So we're able to just get more data because we have better technology. We also have a lot of data that we're collecting just sort of in the course of our everyday life through some of the sensors that we are either using ourselves or we're surrounded by. So you all probably have a sensor on you right now, like your phone. I even have one on my wrist. I have an Apple Watch. So we have all of these different devices that are, all around us collecting data. And these are things that potentially have value for research purposes as well. And researchers have the ability to develop tools like this to gather data that they might not have been able to in the past. We also have an increase in what we could consider born digital data. So typically in the past, in a research lab, you might have something like a lab notebook where you would physically write down. If you went to see your doctor, they would have a chart where, again, they would physically write down. Now that so many things are digital, those pieces of data associated with that are already in a digital form. So it's a lot easier to leverage those for research purposes than if those were things that were collected in, sort of more of a physical medium. There's also things like, social media data that can be used for potentially interesting research purposes. There's some really interesting work on things like biosurveillance and Twitter and that sort of thing. So there's all different kinds of digital data that are being, again, collected or created just sort of in the course of our everyday lives that potentially have research impact. And then on top of the fact that we just have a lot more data, we also have a lot more of that data available. So again, rather than the data sitting inside my file drawer in my lab or on my hard drive of my computer, we have a lot more data repositories, and I'll talk a lot more about this sort of data repository ecosystem where people can make their data available to the public. So when we talk about biomedical data, there are so many things that we can be referring to. There are many different data types. So it's a somewhat complicated ecosystem, and I'll talk a little bit more about working with some of these specialized data types. But this can include all different kinds of things. So things from sequencing data and other what we would consider omics data, sort of these big sequencing data sets. Clinical data that might be collected as part of a clinical trial, or even data that's collected just as part of the course of clinical practice that, with appropriate permissions, of course, can potentially be used in research applications. Qualitative data, so things like survey results or even like focus groups or interviews related to health-related questions, imaging data. So there's lots of different types of data that are part of this, again, sort of biomedical data ecosystem. And this creates some very interesting opportunities in terms of being able to make this available and available for reuse potentially, but also some challenges because we do have so many different types of data that we're dealing with. Again, this piece, software and code, is also important. And this, again, can include a lot of different things. Many researchers are using open source platforms or languages to do their data wrangling and data analysis, visualization, all of those sort of pieces of working with their data. Python and R are both popular platforms for this. There's also code from proprietary programs, so things like SAS and SPSS have code that goes into that. And then there's also either homegrown or commercially developed software. So, either off-the-shelf software tools or sort of bespoke software tools that labs or research groups might develop to analyze or work with their data. So the software and code forms a really important piece of this sort of universe of research outputs as well. So we've got all this stuff, data, software, code. Why is this something that we should make available? Why should we have people go to the trouble of curating their data, making it available, all of this? There's some really good reasons for doing so. One is that having the data and the code available enhances research reproducibility. I'm sure we've all heard about this sort of reproducibility crisis, that people have concerns that the published research can't be reproduced. And when we have the actual underlying data and as well the code that was used to analyze that data or the software that was used to analyze that data, that puts us in a much better position to hopefully be able to reproduce those results. If we can see not just here's what I did and I'll talk about it in the paper, but when we can really get in and see what's going on under the hood, this hopefully helps to increase reproducibility. Having these data and software and other digital research objects available also potentially enables more rapid discovery. So if I have to say I want to start a trial and I have to go and recruit subjects and collect data and come up with a plan to analyze that data, then do that analysis, that obviously is a time-consuming process. If I can come in and find existing data that potentially answers my question, that means that I can go much more quickly than having to, if I had to collect that data again myself. So we have the potential here, when there is data that's available and relevant to be reused, to get to answers more quickly. This reuse of data also increases the return on the research investment. As I'm sure you're all aware, biomedical research is expensive. And so if we're putting all of this money into collecting data, it makes sense to try to get as much use out of it as we can. There's also sort of the argument that not just the monetary investment of collecting data, but also sort of like the human investment of collecting data. If I'm someone who is going to participate in a trial, the researchers, you could argue, kind of owe it to me to make the best use of my data, to make sure that, an illness that I have, finds a cure more quickly, or that other people like me may not have to suffer. So that sort of return on investment in terms of both the financial and the human sort of costs associated with that. And then for certain types of research, having multiple data sets that we can combine is really kind of essential. Certain types of research, particularly things like genomics and these other omics that use these very large data sets, have to have a lot of subjects in order to get adequate statistical power to get results that can be said to be meaningful, just because of how these studies are constructed. So if we are, needing our study to have subjects in the thousands or even in more, it makes sense to try to, rather than me collect all of that data, to see if there's data that exists maybe in multiple places that I might be able to pull in, and therefore be able to get enough subjects for my study, depending on my design type. So now that we've talked about kind of a little bit what we're sharing and why we're doing it, I want to talk a little bit about sort of the policy landscape as it currently stands for sharing of data and other research objects. So NIH has had a long history of really wanting to make public research results available. The NIH, of course, is a federally funded institution, and so taxpayers are paying for this biomedical research. And so taxpayers should have access to that research. So this is sort of a timeline of some various policy developments related to making data and research outputs publicly available. I won't go through all of this, but a couple of things that I'll quickly highlight, and I'll talk a little bit more about these in some of the next slides. The NIH public access policy in 2008 dealt with publications. I'm sure many of you are familiar with and have worked with this policy. The White House issued a memo regarding sharing of research results in 2013. And in the intervening years since then, the NIH has done a lot of work on increasing, the expertise in the workforce for working with data and data science, and also developing tools and platforms for making that data available. Oops, there we go. So a couple of just sort of policy highlights that I'll mention. I talked about that White House memo known as the Holdren memo for short, because it was put out by Eric Holdren, who was the head of the Office of Science and Technology Policy at the time. And this memo, issued in 2013, called for all agencies that fund at least $100 million in research and development, of which the NIH is one, to develop plans to ensure public access to the results of that federally funded research. And this memo specifically mentioned publications, but also digital scientific data. So at the time of that Holdren memo in 2013, the NIH already had a policy in place that met the sort of first half of that, which was with regard to publications. The NIH public access policy applies to all peer-reviewed publications that result from NIH funding, and states that those publications must be submitted to PubMed Central, which is the open access archive of the National Library of Medicine, and it allows for up to a 12-month embargo period. So you're required to deposit your paper at the time of publication, but you have that option if the journal requires it to have that 12-month embargo period before that's made publicly available in PubMed Central. At the time of the Holdren memo, there was also a data sharing policy in place at NIH, but this applied only to grants receiving at least $500,000 a year in direct costs, which is a relatively large amount. That only about 25% of NIH grants met that that mark for that level of funding. And this policy required that if you were getting a grant of that level, that you have a plan for data sharing or explain why sharing is not possible. And they didn't set a specific timeline for sharing data, and it just called for a timely release and sharing of data, which is sort of generally interpreted to be at the time of publication of the research results. Shortly after the Holdren memo in 2015, the NIH released a new policy related to genomic data sharing. And this policy, which is also still in effect, applies to all NIH-funded research that generates large-scale human or non-human genomic data. So things like genome-wide association studies and this other sort of genomic data that, again, for human and non-human. The policy has specific expectations about protection of human data and informed consent. So I think this policy and sort of understanding this policy landscape more generally, there is, of course, the understanding that we're talking about human data here potentially, and it's not appropriate just to put everything online, publicly make it available. So this policy, as well as other policies that I'll talk about, definitely have this expectation that human data will be dealt with in ways that maintain privacy and security of the human subjects, and that people who are participating in these trials are clearly informed in that informed consent about what's going to happen with that data, how it will be shared, if it will be shared, and what sort of protections will be applied to that data to ensure that their privacy is maintained. And then for human data in particular, this policy does actually give some specific guidance about appropriate repositories where you might expect to deposit that data. So for example, human data, it's expected that that will go into dbGaP, which is the database of genotypes and phenotypes at the National Center for Biotechnology Information, which is a division of NLM. And by the way, on all of these, I've given links if you'd like to dig a little bit more into policy, if that's your thing. And I believe the slides will be shared, so you can certainly get a little bit more into the details of all of this. So the most recent development in this area is the new NIH data management and sharing policy. This policy was announced, I guess, last year. It goes into effect in January of 2023, so less than a year now. And it applies to all research that's funded by NIH that generates scientific data. So it doesn't apply to funding that is not generating data. So things like training grants, if I'm developing, training or that sort of thing, or infrastructure, I'm developing, tools or whatever. It includes grants, extramural grants, contracts. It also applies to intramural research projects. If you're not familiar with the NIH, about 80% of our funding goes out to institutions to fund extramural research, and the remaining 20% or so stays at the NIH, and we have a research program that's called our intramural research program. So NIH researchers are also having to do this, not just the ones that we're funding extramurally, and any other NIH funding mechanism that is not labeled above. So the policy requires that grantees submit a data management and sharing plan with their grant proposal. And this plan is supposed to outline how scientific data and accompanying metadata will be managed and shared, and also identify any potential restrictions or limitations that might make it impossible or unethical to share these research outputs. And importantly, the awardee's compliance with the plan as approved by the NIH Institute Center or office becomes part of the terms and awards or terms and conditions of the award. So they are expected to comply with this, and if they do not, their future funding could be affected. So the data management and sharing plan, I'm not going to go through all of this, but there's a few pieces that are expected to be addressed in these plans. First of all, a description of the data that's going to be collected, as well as any metadata and documentation associated with that data, related tools like software and code that you would need to analyze or access that data, standards for the data or metadata, and we'll talk a little bit more about some of those. Timelines for when access to this data will be made available, and plans for how long data will be preserved. Considerations for access, distribution, and reuse, and oversight of data management and sharing. So who on the research team is going to be responsible for making sure that everything outlined in this plan actually happens. Oops. So a couple of things that I want to get a little bit more into with regard to the policy. When we're talking about data for sharing, what are we talking about? So the policy outlines that researchers should plan to share adequate data to validate and replicate study findings. So whatever data somebody might need to go back and replicate that study should be part of what's shared. So things like just summary data, not necessarily adequate for this, because that doesn't give us that full ability to validate or replicate the study. One thing that I really like about this policy is that it also specifies that data that come out of the study but don't necessarily just support a publication should also be shared. So if we have, I do my research and unfortunately I find I have null findings. My hypothesis is proven and I'm not going to be able to publish on that. those data are still potentially important and relevant. And so the policy does call for sharing of those data that, again, come out of the study, but are not necessarily related to a publication. Also importantly, what does not count for sharing. So it's really these sort of final data associated with a study and not really more of the sort of preliminary sort of pieces that go with that. So things like notes in your lab notebook, the actual like case report forms that come out of the participants filling in info, peer review, plans for future research, communications. And also importantly, this only applies to digital research objects and not physical objects. So things like biospecimens or physical samples. As I mentioned, this policy also recognizes that there are certain cases where it's impossible or unethical to share certain types of data. And so there are provisions in place for limitations on sharing. So this may have to do with informed consent. So if, for example, I have a study in process that I've already consented my participants and I didn't address sharing with them, I wouldn't be able to go on and share their data. There are also times that it's just not really possible to de-identify data adequately to make sure that participants can't be re-identified by someone down the line. So in the case where we can't really maintain or guarantee privacy or safety of research participants, obviously that data can't be shared. Where policy or regulation explicitly prohibits it, including tribal law. And then finally, things that are, again, those sort of physical objects or data sets that can't really be digitized within a reasonable amount of time and effort. One other thing I'll say about the policy is that it does also refer to this software and code that may be associated with a study or needed to access the data. So any specialized tools that are needed to access the data should be described in the plan, including names of specific software tools. So I'm going to use, Python to analyze this, or I'm going to use, the R package tidyverse to analyze this, as well as the availability of those tools. So are these open source tools? Are they available for purchase? Do I have to request them from someone? And then finally, the expected lifespan of the tools compared to length of data availability. So if I say my data will be available for 10 years, do I also expect that this tool will also be available for 10 years? So now that I've talked a little bit about sort of, again, what we're talking about when we talk about digital research objects, some of the requirements that are currently in place or are coming with regard to sharing those objects, I want to talk a little bit again about the sort of broader biomedical data ecosystem. And I specifically want to dig into a few challenges and opportunities. There's really a lot going on in this area. It's a very, sort of quickly moving ecosystem and things are changing all the time, but I really want to hit on a few things that I think are things that we should be paying attention to as librarians and potentially engaging with researchers around. So one of the big discussions in the field is not just making data or research objects available, like, okay, I can put it on my website or put it in a repository or whatever, but we really want to make sure, that research objects are FAIR, which stands for findable, accessible, interoperable, and reusable. The dog is very, very passionate about FAIR data. So if you're interested in digging a little bit more into this, there is a paper that this sort of FAIR principles is based on, and I'll talk a little bit more about what goes into each of these 4 pieces. So findability refers to the ability to actually be able to locate a data set, a software object, or the metadata about one of those research objects. Ideally, data and research outputs will have a globally unique and persistent identifier, such as a digital object identifier. And data should also be described with rich metadata that clearly describe what goes into that data set. In terms of this findability, this metadata and data should also be registered or indexed in a searchable resource. So I don't want to just have to have the URL of something to be able to find it. I should be able to go to a repository or to Google or whatever and search for and find that resource. So having a data set or code or software connected with a paper is great, but that sort of findability of that research object as its own relevant output is also important. Accessibility is the second piece, and this refers to the actual sort of like physical ability of a person to access and retrieve data and metadata. So it should be something that is open and free and universally implementable. So things like APIs, application programming interfaces that allow us to interact with repositories or other data resources and use sort of standard protocols, things like FTP that potentially allow us to pull things down. And then importantly, that metadata remain accessible even if the data are no longer available. So there are instances where potentially a data set is not going to be available forever, but we don't want to just get, a broken link or a 404 page not found message if that data is no longer available. That metadata should be forever, so that if I do come to this resource down the line, even if that data is no longer available, I can still get the information about that metadata to know what that data set was. The next piece is interoperability. So this refers to the ability of a user to potentially combine data sets that come from multiple different sources, or to use software that was developed by somebody else. So this refers to formal, accessible, shared, and broadly applicable language for knowledge representation. And you can interpret that language, I would say, somewhat broadly. This could refer to standards, for formatting and collecting metadata or data. This could refer to programming languages. This could refer to the documentation that we use to document our data. So basically, doing things in this standardized way that make it so that other people will be able to understand it, and make it so that it could potentially be integrated or combined with other data sets or research objects that follow the same standards. And then finally, reusability refers to the ability of somebody else to come and reuse that data set. Partly that means that the data set is documented well enough that I can come and understand, like, how is this collected? Where did it come from? Do I know that this is high quality data? But it also refers to sort of that legal reusability, so that data and code are shared with a usage license that explicitly outlines what a person can and cannot do in terms of reuse of that research object. So I want to talk a little bit about a couple of sort of related to these FAIR principles activities or things that are going on, to dig a little bit more into some of the pieces of these FAIR principles. And one to do with this findability is sort of getting a little bit into the landscape of biomedical data sharing, particularly as it relates to NIH-funded research. So the sort of first choice that NIH recommends for data sharing is a subject-specific and open access data repository, and I'll talk a little bit more about that. So repositories that specifically collect data in a particular subject area or of a particular type and make it openly available to people. However, there is not always an appropriate repository for every type or subject of data. So a couple of other potential ways that a person might share research. PubMed Central, that open access repository I mentioned of the literature, also allows for sharing of publication-related supplemental materials, and including data sets up to a relatively small amount. So you can't put huge data sets here, but if you have an article that's in PubMed Central, you can have a data set associated with that. For the sort of mid-level size-wise data sets that are maybe a little bit too big for PubMed Central, there are generalist repositories that will accept data regardless of the subject, of the data type. And so if you have data that doesn't have sort of that natural home in a subject-specific repository, these generalist repositories are potentially a good place to put that. And then for the big data sets, there is the Nih Strides program, which is a program that facilitates partnership with cloud resources. So NIH works with Amazon Web Services, Google, and Azure, which is Microsoft's cloud platform, to enable migration of some existing NIH data sets to cloud platforms, particularly sort of high value, highly used data sets, as well as making some of these resources available to NIH funded researchers. So again, the first choice is one of these subject specific repositories, but if that is not possible for whatever reason, there's other mechanisms by which a person might be able to share their data. In terms of locating those subject specific repositories, there's a few resources that I like to point people to. One is the list of repositories that's maintained by the NIH Biomedical Informatics Coordinating Committee, or BMIC. This page is broken into 3 different parts: open NIH supported domain specific repositories, and other NIH supported domain specific repositories that have some sort of limitation in terms of who can submit data or access data, and then a list of those generalist repositories as well. This page is broken up this way because the list started to get very, very long. So BMIC is in the process of sort of revamping this list and hoping to have a redesigned site and a much more usable list by the time the 2023 policy goes into effect. So I actually maintain this list, so I always like to point people to it, but I think it's a pretty good list of NIH related repositories. Looking beyond the NIH, there are a couple of other resources for locating repositories. One is the Re3 data, which stands for Registry of Research Data Repositories, and they maintain a very large list of repositories that cover a range of disciplines, not just within sort of the biomedical realm, but as you can see, even in things like humanities. So it's a good resource if you're trying to locate a repository for a particular area. Another similar type of resource is Fairsharing.org, and it also maintains lists of repositories and databases where you might be able to find or share data. And one of the things that I also really like about this resource is that it includes information about standards as well. So I can go to my list of repositories, find the one that I want, and it's documented here with like what kind of standard for metadata or reporting is expected if I'm going to be submitting data to this repository. So another resource for kind of thinking about where to share data. This is an output of the Office of Science and Technology policy, and it's included as an appendix or supplementary information to the NIH data management and sharing policy. And it's a set of desirable characteristics for repositories that is designed to, for one thing, help researchers to kind of assess a repository that they might be thinking about for depositing or locating data. And it's also kind of guidance for people that are maybe thinking about developing repositories or program officers who are thinking about funding repositories to sort of set some standards for what we expect for high quality data repositories. And again, I won't go through all of this, but have shared some links. And basically this just sort of identifies some best practices for repositories in terms of what we would expect for maintaining sustainability of the data, encouraging and enabling fairness of the research objects, enabling reuse of the research objects, as well as enabling tracking of that data reuse, which I'll talk a little bit more about, and then important things like security and privacy. There's also a set of additional criteria for repositories that are going to be housing human data, where there's sort of a higher bar for maintaining privacy and security for that data, as well as this concept of fidelity to consent. So in some research data sets and some sort of research applications, there may be restrictions that are associated with reuse of the data. So for example, if you look at dbGaP, that database of genotypes and phenotypes, there are certain data sets that, because of the way the participants were consented in that original study, the data is only allowed to be reused in a particular context. So this data set can only be used to study eye diseases, and you can't use it to study mental illness or something like that. So there are, in some cases, again, in line with the original consent of the participants, restrictions about what can and can't be done with data. And so that is one of the pieces that is something that is sort of expected for repositories that deal with human data. And most of these are things that we would expect that, there would be some data access committee that would be reviewing requests for data and making sure that they are in line with what is allowed for the data set to be reused. So I mentioned those generalist repositories, which can be a useful solution if there's not an existing subjects specific repository that's relevant. And I want to just briefly mention a relatively recent initiative of the NIH, which is the Generalist Repository Ecosystem Initiative, which was created to sort of enable these generalist repositories to work together on areas where they have sort of similar interests, and also to help make access to NIH-funded data and discovery of that easier. So we're expecting that this will make it easier for researchers to share their data, particularly once that January 2023 policy goes into effect. It'll make it easier to sort of search across repositories and also locate NIH-funded data within those repositories, help, again, make data available for reproducibility and also that secondary use of data. This just talks a little bit more about sort of the goals and activities of the GRAE, the Journalist Repository Ecosystem Initiative. So the repositories will be looking at how they can better align with those desirable characteristics that I just mentioned, implementing features for better discovery of NIH-funded data, developing consistent metadata models across the repositories, which will enable, sort of set the technological table for potential down the line of federated search or search across those repositories. There's also a piece around education and outreach, and the sort of overarching theme of this initiative is co-opetition, which is the sort of a mashup of competition and cooperation. So recognizing that there are areas where these generalist repositories sort of have unique offerings that they compete with each other on, but that there are also things where they all have kind of shared goals and can cooperate on. And the goal of this initiative is to really kind of explore and give space for those repositories to work on those areas where they have that ability to cooperate. And then these are just the 6 repositories that are part of the Generalist Repository Ecosystem Initiative: Dataverse, based out of Harvard; Dryad, out of the University of California; Figshare, Mendeley Data, the Open Science Framework, and Vivly, which is a generalist repository that specifically is focused around clinical trials and therefore some of that sensitive human data. So I want to dive as well into a little bit interoperability and specifically touch on common data elements, or CDEs. So there's a lot of types of research, particularly things like genomic data, that are sort of by their nature and intentionally when these data types were created, very much interoperable. So there are very clear standards for collecting genomic data sets. And whether I am here in the US or in France or in wherever I might be around the world, regardless, I'm probably using the same standard. So that means that these genomic data sets are sort of by their nature going to be interoperable and can be integrated. The same is not true for clinical data, and that is where common data elements come in. So common data elements are a fixed representation of a variable comprising one defined question that is paired with a set of allowable answers or a form for allowable answers and used in common across multiple sites or studies or initiatives or whatever, the common piece, just that it's used in more than one place. So an example of this might be if I want to collect the height of my participants. There's a lot of different ways that you could do that. You could do meters, you could do feet, you could do feet and inches. So common data elements, again, specify that clearly defined question and what answers are allowable for that. So maybe we specify that in this common data element, we're going to collect height in feet and inches in whole numbers. And we're going to use it across all sites that have funding for a particular project. For those sorts of variables, it's, you could imagine that even if I did collect height in meters, it would probably be easy to make the conversion. But I think these are particularly relevant when we talk about things that are a little bit more subjective in nature. So things like defining emotional states or quality of life or, self-perceived health. So a question like, how often do you have fun with friends? Might be paired with these allowable answers, always, often, sometimes, rarely, or never. And again, this sort of gets at a question that's a little bit harder to quantify in numbers. And so it makes sense if I am going to be doing research that asks these kinds of questions, if other people also ask that question in the same way, that means that we have data that are going to be comparable. These CDEs can also come not just as individual questions, but also as bundles, such as case report forms. So I define for my clinical study a set of data that's going to be collected for every single participant in the same way. Or it might be things like validated survey instruments that have to go together to keep their validity. So something like the PHQ-9, which you see here, which is a tool for assessing depression severity. So again, if we collect this data in the same way across multiple studies, that means that we would be able to integrate this. Whereas if we just said, collect information about depression, you can imagine that different researchers might sort of operationalize that in different ways. So using these CDEs ensure that we're all kind of comparing apples to apples and oranges to oranges. This means that we, again, would be able to integrate some of these studies. So if study A and study B both collect data in the same way, we're able to compare those. We're able to potentially group those together to do a meta-analysis. And another thing that I haven't mentioned on the slides, but I think is really important for common data elements is that it also, by requiring certain common data elements, it allows NIH to say certain things that we care about making sure that people are documenting in their studies, like things about the race and ethnicity of participants to ensure that we're getting diversity in our research studies. And I think it's really important to make sure that these common data elements are created in collaboration with the research communities who are going to be the ones answering these questions. If you were at the previous keynote or plenary talk, I think that was a really great example of why that's so important. And so yeah, there's a lot more I could say about that, but go listen to the previous talk if you haven't. So another piece that I want to touch on is this reusability piece, and particularly thinking about curation. So one model for thinking about data curation is from the Data Curation Network. And this sort of describes their process for going through and making sure that data is complete and well documented, which makes for clear data that would be something that somebody could come down the line and reuse. I want to address briefly just sort of the cost that's associated with this curation and what it takes to enable this reusability. This data management and sharing policy does allow researchers to include costs in their budget for things like data curation and doing the work of developing documentation, as well as management during the project. So, on my computer or whatever, and preservation and sharing in repositories after the project is over. So sort of that long-term deposition of that data. It can be a little challenging though to figure out if I'm, sitting here at the very beginning of my project, I'm writing a grant proposal, how do I know what to put in for curation? So I want to point to a resource that I think is really helpful for thinking about this, which is a report of the National Academies about forecasting costs of biomedical data. This was a long-term study that was funded by NLM, and they did some work to develop a framework for forecasting costs and sort of what we should be thinking about as we're thinking about those costs. So they point to these 3 data states. So we have data that is, sort of live and active. We're collecting the data, we're actively managing it. And then we have this sort of active repository and platform. So maybe we are done with the sort of initial capture portion of this and we make it available in a repository. And then eventually we might move it into some sort of a long-term preservation platform where it's sort of archival or cold storage. And these data sets may move between the 3 different data states, and there's different costs associated with activities in each state. In the interest of time, and I'm not going to go through all of this, but this is sort of the framework for thinking about those costs. And I've, again, given some links to the report and some of the sort of deliverables that go along with the report if you're interested in diving into that. One other thing that I'll say about reusability is just sort of thinking about reusability for code and software. The NIH has given some guidance about best practices for sharing code and software that I won't go into there, but I do want to just quickly mention that reusability of software is not necessarily trivial. My colleague Miriam Zering-Helem and I did a workshop on reproducibility a couple of years ago, in which people tried to reproduce results from the research. And what we found is that it's really difficult. Even studies that, shared their software, shared their data, there's a lot that goes into documenting all of that is just not easy to do. And so it can be really challenging to sort of reproduce some of that. I am going to skip past this and just really briefly talk a little bit about quantifying impact. So if we're going to be having people doing all of this, we want to be able to give people credit for sharing data, for sharing code. When you write a research article, you sort of get credit for that in the form of people cite your paper and you can say, look, this has been cited, 500 times. It's really important, demonstrating impact. It's a little bit harder to do that at this time with digital research objects. So the data citation principles point to some ways to do that. And basically, I'm going to skip past this, but right now we don't have really good ways of doing that. So I think this is an area that's going to be important to do work in the future. And I'll just close with a sort of advertisement for an event that we have coming up next week that I think it would be great for you to share with your communities if you're able. We're doing a webinar series in collaboration with the Data Curation Network and also the network of the National Library of Medicine's National Center for Data Services. And we're going to be focusing on sort of different stakeholders. And this first one is intended to be an introduction to data curation and services for researchers. And one of our big goals with this is sort of raising the awareness among the research community that librarians can help with all of this stuff. So if you are hoping to sort of make researchers at your institution more aware of things that your library can offer, this could be a good way of doing that. So I will stop there and ask if there are any questions.
Thank you, Lisa. That was a fantastic talk. We did have a couple questions come in. First was, hang on one second, I want to make sure I get it right. Do you know of any resources or literature addressing ethical issues around data sharing? In particular, how data might be collected for a specific reason, yet then due to sharing policies is now available for research that is not related at all and may be used for questionable work. An example might be studies related to sex differences in all types of areas being taken and used against transgendered individuals. Thinking about news about student athletes right now. Of course, there are other examples.
Yeah, that's a really great question. And I can't point you to a specific article off the top of my head, but I will say that is definitely something that is a concern in the research community. One area that I know there's been some study on is looking at like social media data. So I mentioned some of like, you can use Twitter and find out. There have been studies that looked at like college students tweeting about drug use around finals week. And it's like, okay, yeah, you did put that out there on Twitter. That's a public platform. But is it ethical for me as a researcher to now use that in my study? You didn't consent to that. So there's definitely some interesting ethical questions there that I think are very, very important to dig into.
Sure, absolutely. Thank you. And there was another, is there a reason why Zenodo is not on the NIH list? And could you suggest general repositories that support the use of a DUA or other sign-ins to access the data? I guess that's two.
Yeah, so Zenodo is on the repository list. They're not part of the Generalist Repository Ecosystem Initiative, although I think we are going to be engaging with them. There are background reasons why they are not part of the initiative. They didn't really have the bandwidth to participate, but they are on the list of general repositories that we share. And then what was the second part of the question?
Can you suggest general repositories that support the use of a DUA or other sign-ins to access the data?
So I'm not sure if any currently support that, but I think that is something that we're going to be thinking about with the Generalist Repository Ecosystem Initiative. So that could be a development in the next year or two.
Okay, great, thank you. Can you describe differences and similarities between metadata and standards and CDEs?
Oh, that's a long answer to that question.
That's a whole other topic, I think.
Yeah. So I would say they're sort of, that's a very big Venn diagram, right? So metadata is an example of a standard. There's other standards for things like how we represent information in electronic health records and exchange data. That's called FHIR, Fast Healthcare Interoperability Resources. CDEs, you could say, are a type of metadata because they sort of document how data are collected. So I think a lot of times those terms can be thrown around somewhat interchangeably, but again, it's very much a Venn diagram of like overlap in terms of how those terms are applied.
Yeah, absolutely, absolutely. And then I'm not sure if this can be clarified anymore from what you did or not, but the question was, which of the repositories will be most secure? Is there a way to determine that?
So I would point back again to that guidance with regard to desirable characteristics for repositories. I didn't include all of it on my slide, obviously, but there is a little bit more guidance, particularly with regard to the additional 9 criteria for human subjects. So I'm not aware of any sort of like list of like, these are good, these are not. But most repositories will document sort of what their security practices are, so that you would be able to hopefully tell based on this guidance whether a repository meets the criteria or not.
Great, thank you. I've saved the chat and I will send that to you, Lisa, just so you can see, because there was some discussion going on that wasn't really questions, but I think you will find interesting. I want to thank you again for your time with us today. I greatly, greatly appreciate it. Again, their attendance was really great for this, so I think lots of interest from other folks also. Everybody else, again, the recording of this will be made available after the symposium. It may actually be up sooner than that. I can't I can't promise you when, but soon. And check out the nnlm.vfairs.com website to see what else is coming up for the rest of today and tomorrow. We hope you'll stick around for the rest. Oh, and I want to give a plug for the closing keynote. John Eldridge is going to talk a little bit about something that Lisa alluded to as ways to incorporate librarians into research. So he's going to have some tips on how to do that. And if there are researchers here listening, ways that you may be able to think about incorporating librarians that you haven't done before. So I just wanted to stick that in since I had some inside knowledge of what John's keynote is going to be. Thank you again, everyone. Really appreciate your time and attendance and attention.
Thanks.
Thanks, Lisa. Thank you, Christine.